Supervised learning is probably the most well understood machine learning technique among these three. But there are also some well-known applications of unsupervised learning, and I want to look at one case of those, which is the k-means algorithm, which is very widely employed. And what this is useful for is clustering, basically. So suppose you have, again, some big data set, and you just want to know whether the items in that data set, say the cases, fall into some recognizable clusters, so that some of those cases are more like some other cases than they are like others. And then ideally what you want to do is once if you can, in an automatic way, using k-means, for instance, if you can parcel that data set into, say, the 5 main clusters, okay, using an automated process, that will ideally give you 5 clumps, 5 clusters, 5 groupings of the cases in the data set, where each of those groupings have a large number of things in common, and where at least they have more in common with each other, items within each of those groups, than they do with items outside of those groups. And so then you can look at those clusters and you can ask, well, what is it that makes those clusters, what is it that kind of defines each of those clusters? What makes this set of data points different from this set of data points? What makes this set of cases different from that other set of cases over there? And so it's a useful kind of exploratory method. In order to apply this, one can just follow the steps listed on this screen, which I think are pretty intuitive. But there are a couple of potential problems that need to be paid attention to. So one is that the researcher, the one running the program, has to decide at the outset how many clusters they want the program to parse the data into. And that can lead to, that can be somewhat arbitrary, or that can make a big difference in the results that one sees. So normally what researchers do is they vary the number that they set k to, and they run the algorithm multiple times. So they see, does setting k at 5 produce a natural kind of breakdown of the data? Does setting the k at 7 do that? And so on. And there are some mathematical estimates of how much similarity or difference is being captured by the algorithm after running it at k equals 5 or k equals 7 or k equals 12, etc. Okay. So that's one issue. Another issue is that the first step of the algorithm's performance after the desired number of clusters has been selected is that it picks random cases to treat as the centers or centroids of groups. And that's only a starting place, because then it goes through multiple iterations wherein the centroid in each group gets moved, and then sometimes cases get shuffled differently between groups. Cases end up kind of moving from one group to another, if that makes more sense in a further iteration of the process. But the initial placement of the centroids, which is random, can sometimes lead to distortions. And again, the usual way of handling that problem is just to run the algorithm multiple times and see whether there's some convergence on, similar clusters, even after having run it several times. And if the clusters look very different in 1 out of 5 times that you've run the program, then that suggests that that's an outlier or a distortion, whereas the other 4 are more revealing about what clusters there really are, or similarities and differences there really are in the data. And 2 other potential problems that are a little bit tricky are that because what this program is doing is trying to find data points that are close to one another across multiple parameters, or multiple dimensions. You can think of it like what it's doing is it's making a multi-dimensional map and putting each of the points in that multi-dimensional map. We're very familiar with three-dimensional maps, x, y, and z coordinates, or two-dimensional maps, x and y coordinates. Dimensional maps that go beyond 3 dimensions are hard to imagine and represent, but they're certainly conceivable and they're mathematically describable. And so if you have a data set with, let's say, 12 parameters, then it's like a 12 dimensional space. And each data point is put somewhere within that 12 dimensional space. So what this algorithm is doing is clustering. It's saying which data points are more like others within that 12 dimensional space based on how close or far away those data points are from one another across each of those dimensions. But what that means is that if some of those dimensions just have larger number values than others, then the distances there will look larger and will pull data points apart from one another more than what are, in terms of the maximum and minimum values, equally distant or similar points as measured across other dimensions. So what you have to do is you have to normalize the parameters so that you don't get that kind of distortion. But that's a fairly well understood kind of procedure to undertake. Another problem that has to be avoided is that if some of the parameters are not independent of one another, think for instance of height and sex and in humans. So there is some correlation between height and sex, male or female. And if you were to use both of those data points in a k-means, both of those parameters in application of a k-means algorithm to a clustering task, then you may get some, you may see some distortion in the groups that are produced, because it's like you're taking a single factor and amplifying its import in terms of how close or far away various data points are. And so that amplification, then it means you're sort of losing informational value from the other parameters because some parameters are being overrepresented. This is a harder problem to deal with and sometimes takes some thinking about how the various parameters in the data set are related to each other. The last of these techniques, reinforcement learning, has applications in robotics and the programming of or training of autonomous vehicles, and in video game playing, artificial agents. So if you want to train a program to be really good at a video game, reinforcement learning might be a good choice. And it's interesting to speculate about why this training procedure works well for those three kinds of problems. It may have something to do with the value, but also difficulty of predicting or in advance encoding small changes in movement and the success effects of those small changes. It may also have to do with the difficulty of being able to, that there's a lot of information value in gauging performance by a certain kind of success, but there isn't enough information prior to the training that's had by the human researchers about what the available courses of action are for meeting that goal. And so it's better to allow the system to basically discover effective ways to meet the goal. And sometimes these systems will discover effective ways to meet the goal that are really surprising from the standpoint of the human researchers, because they wouldn't have thought to program that into the machine. Okay, I think that's enough for covering the basics of machine learning for this course. Of course, it's a fascinating area of study, and it is very active right now. And I encourage anyone who's interested to dive in deeper using other resources. But these lectures and the readings for this week cover what we are expected to know about it for purposes of this class.